Hi, we are Group 2 Subgroup 6. Today we will be presenting bioremediation of heavy metals by using the microalga Desmos subspeciatus. To begin with, heavy metals are usually generated from ore recovery by mining industry using fresh water and hence results in pollution. Desmos subspeciatus is a freshwater green alga with the ability of heavy metal absorption. The study was conducted to find the optimum conditions for effective bioremediation of heavy metal by these subspeciatus. The study was divided into 4 stages, namely inoculation, growth study, pH study, and contamination study stages. In inoculation stage, stock cultures were prepared by incubating single cells isolated in photobioreactor. In growth study stage, the growth and development of these subspeciatus was observed and analyzed. In pH study, pH sensitivity of these subspeciatus for heavy metal bioremediation was examined at pH 3, 5, and 7 as most heavy metals are insoluble at high pH. Contamination study stage observed parameters on control cultures and heavy metal contaminated cultures added with arsenic, cadmium, mercury, and lead. Growth parameters, which were chlorophyll A measurement, optical density, cell count using Thoma chamber, and suspended particle count using Coulter counter, were observed in all the stages. Nutrient levels, phosphate, ammonia, nitrate, and nitrate were investigated from growth study stage onwards. Samples were frozen to determine the dry matter of cells before and after treatment in pH study and contamination study stages. Bioaccumulation of cadmium, mercury, and lead by these subspeciatus showed lower efficiency than that by Cholera vulgaris, but more arsenic removal was observed. Although initial bioabsorption of lead by these subspeciatus was greater than that of Cinedesmus quadricauda, lead content was released back to extracellular environment. This could be due to equilibrium of heavy metal concentration between intracellular and extracellular environment. Infection by bacteria or fungi could also disrupt chemical bonds between algal cell and heavy metals. Initial uptake of arsenic, cadmium, and mercury of these subspeciatus was similar with that of S. quadricauda. These subspeciatus showed the highest final heavy metal uptake on cadmium, followed by mercury at 24.5% and 21% respectively, but was lower compared to other studies with average uptake of 73.2% and 66.7% using other photosynthetic microbes. Initial and final uptakes of arsenic were similar, while initial uptake of lead was high but its final uptake was insignificantly low. These subspeciatus showed higher density but lower heavy metal removal at pH 3 compared to at pH 5. Heavy metals, which are highly soluble at low pH, diffuse excessively into cells causing stress, thereby causing cells to deteriorate. The concentration of nitrate and phosphate in cultures inside light incubator increases more than that inside greenhouse, denoting that life cycle of these subspeciatus culture was faster and decay was observed. In conclusion, these subspeciatus showed good initial bioabsorption of mercury and lead. It was suggested to carry out short-term these subspeciatus culture for effective heavy metal bioabsorption, as long-term heavy metal uptake was inefficient at pH 5. It was anticipated that pH value between 3 and 5 could be suitable for bioremediation with better availability of uptake and higher heavy metal solubility.
Now we are moving to the first section of reflection, which is benefits. The benefits of this research are: this subspeciatus is suitable freshwater green alga to remove heavy metal, which is as good bioindicator. It is because it has the ability to change its form because of the alteration in environment. Besides, this subspeciatus is fast adapted with new environment and different pH condition. In the result, it showed the best cultivation of microalgae were in high acidity of pH 3 and pH 5. Other than that, the culture also adapted well to the natural lights and temperature changes. Next, the heavy metal uptake by the subsplicatus biomass was not efficient at pH 5 since the final uptake were 50% as 7% lead, 24% cadmium, and 21% mercury respectively. However, its initial bioabsorption showed good results, especially lead less than 79% and mercury less than 63%, which reflects their potential as a good remediator. The bioremediation by these subsplicatus has the potential to accelerate the production of clean biomass, which can enhance the economic value in the form of bioenergy. This is proven by the biomass growth 21-fold after 14 days compared to the starting culture. Moreover, this subsplicatus has a huge potential as bioabsorption in short-term uptake. Nevertheless, the bioabsorption efficiency can be increased through the application of immobilization and pre-treatment. In the case of short-term application for bioabsorption, calcium alginate bed can be utilized, while for longer time bioaccumulation, the agar carrageenan could be used in conjunction with the subsplicatus to enhance the natural bioremediation process.
Next is the limitation. The Desmodesmus suspicatus can only be used for the absorption of lead and mercury at initial level. High amount of the initial heavy metal concentration were missing from the final culture. The concentration of heavy metal were not found from both of the media and biomasses. This could happen because they might have been absorbed by the reactor's glassware or has been vaporized. Next is the long-term uptake of heavy metals such as arsenic, lead, cadmium, and mercury was not efficient. This is because the use of the S culture is only for short-term bioabsorption of heavy metal. The fourth one is most of the initially bioabsorbed amount of lead was not absorbed properly and released back from the biomass. This happened because of some bacterial infection that caused the disruption of bonds between algal cell and heavy metals. Lastly, the Desmodesmus suspicatus was not efficient at pH 5. The heavy metal became less soluble when the pH level is getting nearer to the neutral condition. Thus, at pH 5, only some of the metal concentration was available for cellular uptake.
This will be the last section where I'll be discussing all the business suggestions in order to improve this research. So one of the ways is by introducing only one or two heavy metals at a time to the Desmodesmus subsplicators. For instance, introducing cadmium and mercury first. This will decrease the high alkalinity, which is toxic to the microalgae, and also improve the uptake of heavy metals as well as its solubility. The second suggestion is by introducing Desmodesmus supplicators together with another microalgae, for instance, Para cholera foci, or introducing together with another microorganism such as fungus. For the example of fungus are Pleuratus, Aspergillus, and Trichoderma. This will improve the uptake efficiency of heavy metal, especially arsenic and cadmium, since Desmodesmus supplicators is inefficient of bioabsorption of these metals. The third suggestion is by ensuring Desmodesmus supplicators is supplied with sufficient nutrients, for example, ammonium, nitrogen dioxide, nitrate, and phosphate. This can be done by constantly monitoring from the beginning until the end of the control experiment. For a case whereby the microalgae is lacking one of these nutrients mentioned, the uptake efficiency of these heavy metals will be affected. The last suggestion is by maintaining the moisture content of desmoidesmous supplicators at a favorable level throughout this experiment. So this will prevent from causing stress to the microalgae, which will disrupt its bioabsorption of the heavy metals. That is all for me. Thank you.